All right, clip number 2 on section 5 notes on angle relationships in circles. In this clip, we're going to focus on 3 examples, one highlighting each of the 3 theorems or each of the 3 scenarios about where an angle can be located. And really just to demonstrate like how things will be plugged in, different variations of what we might see for each of these. But again, what will be the first priority is first locating where is the angle. Once I know where the angle is located, that will dictate which of the 3 formulas I'm going to use. And then after that, it's just plug in what I know, solve for what I don't. And in some cases, I just have to look back at what a question was asking for just to make sure I'm not just solving for x or some variable. That if it's asking me to like plug that back in to find a specific measurement of a geometric object, that I make sure I do that as well. All right, so the first example we're going to focus on for this clip is over here in the margin. In this case, again, I see a circle, surprise, surprise, and I get an angle that is created fundamentally with this chord AB and line M. So the first thing to be able to identify is where is the angle located? Where is the wedge located? And hopefully it's obvious here that the actual angle location is on the circle itself at point B right here. The other thing to be aware of here that they tell us in the instructions is that this line M, they don't always have to name a line after 2 points. Sometimes they just give it like a little italicized letter. But line M here, they tell us is tangent to the circle, meaning it's only going to touch the circle at one spot, namely here at point B, what we would call the point of tangency. So this is literally just a version of this first theorem where I have a tangent and an intersected chord. So I know I'm going to be dealing with this kind of formula base, depending on what I'm solving for. I'm going to be taking half of an intercepted arc measure. The other thing to be aware of here is that this is technically just an extension of what we did in section 4 on the inscribed angle theorem. Both angle 1 that is written out here and its supplement for whatever angle this will end up being over on this side. In either case, it's what we would call an inscribed angle because the angle itself is located on the circle. So fundamentally, angle 1 measurement that we're going to solve for first is going to be exactly 1/2 of its intercepted arc, which will be arc AB here on the left. So in this problem, we're going to be asked to solve for the measurement of angle 1, and then in part B, you're going to be asked to solve for an arc measurement. In both cases, they're measured in degrees. It's just a matter about the calculation in which direction we're solving for. We'll see both right here. All right, so let me jump to the whiteboard to quickly solve this one, just so I can blow it up a little bit and we can zoom in on it. All right, so for our first example, we're given the following. We got a circle. We have a line tangent to the circle at a point B. This is line M. And then there's some chord that is created here that connects to that B to A. Then we're told to solve for angle 1. Angle 1, we're told, is this little wedge angle down here in the corner. Sometimes they'll number the angles just for like location's sake. So we would title this angle 1. You'll notice there's not a third letter over here to make that like 3-letter angle version. I wouldn't call it angle B either because technically there are 2 angles here to choose from. So angle B would be kind of confusing if it were given that name. But in either case, we're told that that's angle 1. And then the other piece of information we're told is that over here on the left, this arc measurement is 130 degrees. And just to point this out again, just because you're going to see this in geometric diagrams, if the degree measurement is outside of the circle, it's referring to an arc. Okay. Whereas if they were to tell me a degree measurement here inside of this wedge, that would tell me the actual angle measurement. All right. But anyway, the actual formula here, because this is an inscribed angle, because I get this scenario of a tangent intercepting a chord, I'm going to end up with the following formula geometrically. The measurement of angle 1, which is technically an inscribed angle here, this is just going to be a direct reference to section 4, is going to be 1/2 of its intercepted arc. What's the intercepted arc for angle 1 here? From B up to A. So measurement of arc AB, whatever that measures in at. So geometrically speaking, this is just the formula I would use. I'd plug in what I know, solve for what I don't. So I'm actually going to know exactly what arc AB is. That's going to be that 130 degrees. Okay, be prepared. Sometimes they'll give you an algebraic phrase. In either case, I'm just substituting in whatever that arc measures at. So when I do that, I get the measurement of angle 1 is 1/2 of that 130 degrees. You could either multiply it by 1/2, divide it by 2. It's the same exact thing. In either case, we get to the same result. Measurement of angle 1 is going to be 65 degrees. Perform it on a calculator. Don't be intimidated of that. But that part's done. Super quick and easy. Again, not really heavy on computation here. So just to kind of branch off a couple of things here. First off, that tells me angle 1, which is the measurement of this wedge right here. It didn't ask me for it, but if I wanted to find out the angle over here next to it, first off, because this is a straight line, this tangent is one continuous line, that forces both angle 1 right here and whatever this angle is to be supplementary. They have to add to make 180 degrees because every straight line is a 180 degree measurement. It's what we would call a straight angle. So I could simply subtract 65 from 180 to figure out what this other half of the angle was, if that's what they were asking for. And that would directly help me with figuring out this major arc AB as well. All right, but for part B to this margin problem, they ask me now for this arc. And I forgot one other point that they drew in the diagram. Because it's a major arc, they threw in some random point C over on this side, because now I can call this major arc ACB or BCA. In other case, it's this other side. But they asked me about figuring out the measurement to that side. Now I could go through the effort of figuring out the supplement to angle 1, to figure out this angle here, and then doubling that to figure out this major arc. But the actual simplest process here is I know that every circle has to have 360 degrees around it. Well, this is fundamentally just split up into two pieces. If I know one piece, I can figure out what's left over for the second. So algebraically speaking, I could just say this. Measurement of arc AB, which is that minor arc that I'm given here, 130 degrees, plus the measurement of arc ACB, which is just the other half of that circle. Those together have to make 360 degrees, so I could just do 360 degrees minus the 130 to figure out what's left over. And what we'll quickly find out once I plug in the 130 degrees, just to show the algebra here, plus measurement of arc ACB. To do what many of you would do in a single step, I would simply subtract the 130 from 360, and I'd find out that that major arc is the remainder, or the leftover 230 degrees. Not terribly difficult in either of those cases. Great. So this is an example of what happens if the angle is on the circle itself. That angle is simply going to be 1/2 of an intercepted arc. Great. Example number 1 done. Now down at the bottom of this first page of notes, we have 2 more examples. And sorry if they get a little small. So again, just kind of a good representation of what you'll see in your section assignment or on a test, hint, hint. And when you're asked to find the value of a measure of an angle, which we are asked to do in both of these cases, in this section particularly, really the first thing to do is identify where is the angle located. On the last problem that we did, the last example we did, the angle, the vertex of that angle was located on the circle itself. So that dictated which formula I had to use. Hopefully you can distinguish between these 2 examples. This example, part A, over here on the left, the angle is quite obviously located on the inside, the interior of the circle. So that's going to dictate which formula I use. Part B obviously looks a lot different. The angle is quite obviously outside of the circle, which again will dictate which formula I use. As long as I know where the angle is located, I know what formula I have to use, and then just plug in the stuff I know, solve for the pieces I don't. So let's do that. Part A, I'll try and keep it on the screen right now so I don't have to redraw the diagram. But part A, angle is located on the inside of the circle. So fundamentally, I'm going to be taking an average arc length right now. Because if I'm asked to solve for x right here, this angle, this slice, so to speak, on the bottom of the pizza. If I'm asked to solve for that angle measurement, there are technically 2 intercepted arcs right now. There's the obvious one, the one that's directly across from that slice, this 156 degrees for arc KL that they described for me. But then directly behind it, there's another intercepted arc, the slice directly behind it, from J to M, which they also happen to tell me measures in at 130 degrees. So unlike the last example where the angle was on the circle itself, there's more than one arc that is created by this angle. And so I need to take the average of it. So algebraically speaking, for part A, I would have the following. The measurement of angle, we'll call it X right now, even though that's just what the variable is. We'll call it angle X. Is going to be 1/2. It starts the exact same way regardless of where the angle is located. There's going to be a 1/2 multiplied by something. In this case, it's just multiple somethings. And because the angle's on the inside of the circle, these somethings are going to be added together. So again, this is part A. For part B, it's going to look exactly the same. It's just that this part right here for part B is going to end up being subtraction. Okay, but back to this problem, part A. I need to take the average of the intercepted arcs. Well, looking back at my diagram right here, the intercepted arcs are going to be arc KL down here on the bottom. That's the more obvious intercepted arc, the arc that's created by the slice itself. The one that's a little trickier to find, maybe not trickier, but the one that's a little less obvious to find is the one that's directly behind it, arc JM here on the top. So algebraically speaking, I would plug those in. That would be measurement of arc KL on the bottom, and the one behind it, arc JM. I didn't have to worry about adding two angles together with an inscribed angle because there was only one intercepted arc that I could choose from. There was nothing else to confuse it with. All right, well, in this case, I just solve for the pieces. I plug in the stuff I know, solve for the pieces I don't. So measurement of angle X here is literally what I'm solving for. It's X degrees. Be aware that it won't always just be X. Maybe it's like 5x minus 7 or something like that. So whatever it is, it's just you're setting up yourself with the traditional algebraic equation. But I'm going to take 1/2 of the sum of those arc measures. I happen to be told what both of those are explicitly. Arc KL is 156 degrees. JM is 130. I'm literally taking the average between those two numbers. So when I do that, I add the two numbers together. That gives me 286 degrees. If I multiply that value by 1/2 or divide it by 2, I get the same result either way. And in this case, X is just explicitly going to be this result, which in this case is 143 degrees. And that problem's done. Really just being able to identify what you need, right? Plug in what you know, solve for the pieces that you don't. Okay. For part B, let's go back up here so you can see this second example. For part B, now the angle is going to be outside of the circle itself. So fundamentally, that's going to change what formula I'm using. So for part B now, angle is outside of the circle. It's going to start very similarly. The measurement of this angle on the outside, which in this case now has like an actual name, that's measurement of angle C, is again going to start by multiplying 1/2 by something. And those somethings, in this case, again, I have two arcs that are created on the inside of that angle. Okay. So in this case, now because the angle is on the outside of the circle, these somethings are going to be subtracted. And in this case, just to write it in, that's going to be the larger arc minus the smaller arc. Always the larger minus the smaller. So in this case, that's going to be arc AD, or DA, whatever you call it, and then measurement arc BD is the smaller of the two. Whatever happens on the inside here, I should end up with a positive number. Okay, if you got a negative, you just did the wrong order. Okay, but anyway, when I plug these values in, arc AD here is 178 degrees. I'm going to be subtracting 76 degrees from that, just to kind of fast forward through this this process right here. So measurement of angle C happens to, again, just be the X itself. Well, 178 minus 76, that's going to give me 102 degrees. I could multiply that by 1/2 or divide it by 2. It's the same exact thing. But in either case, I get X equaling 1/2 of 102, which is 51 degrees. So x equals 51 degrees. That exterior angle, the one outside of the circle, equals 51.